The retina has evolved and specialized in such a way that it can carry out two very distinct functions, which are embodied in two types of photoreceptors, rods and cones. These are the biological equivalents to pixels in a digital camera. While rods and cones are structurally similar, both types have an outer segment, inner segment, and synaptic terminal, they're functionally quite distinct. Rods have allowed us to detect low light levels that we encounter at dusk and dawn, while cones have evolved for higher light levels and for the detection of color between sunrise and sunset. Regardless of the time of day, however, the retina does not accurately represent absolute light intensity that falls onto it. If you've ever looked at a sunrise or sunset and then tried to capture the same picture with a camera, you might have noticed how many more levels of light your eye is able to perceive as compared to a camera. This is known as dynamic range. The eye has a remarkable dynamic range. The retina has evolved to detect differences in the intensity of light falling on different parts of it, which is a crucial distinction we'll explain in a little while. But back to photoreceptors. How do these photoreceptors work? Basically, the process is simple and involves conversion of electromagnetic to chemical to electrical energy in a sequential cascade. This process is known as phototransduction. As photons enter the eye and fall onto the retina, they're absorbed by photoreceptor cells in the outer segment and transduced into chemical energy. Subsequently, this chemical signal is converted into an electrical signal through the change in membrane potential in the inner segment. And this signal is changed back into a chemical signal again at the synaptic terminal. Electricity is the universal language of the nervous system, and all of our sensory systems have evolved to achieve the transduction of sensations into electrical signals. To help us understand how this all happens in the visual system, we'll start by examining rods, which outnumber cones in the human retina about 20 to 1. But most of what is known about phototransduction in rods applies to cones as well. As we've learned previously, one way by which information flow is represented in the nervous system is via changes in the membrane potential of neurons. Phototransduction can convert light energy into changes in membrane potential in the photoreceptor cells. In many ways, this process is analogous to the transduction of chemical signals into electrical signals during synaptic transmission, but with one key difference. Rather than reacting to a chemical ligand, photoreceptors have the capacity to react to electromagnetic energy in the form of photons. The details of the mechanism by which this interaction can occur delves further into chemistry and physics than will go in this course, but suffice it to say, certain molecules can absorb photons at particular wavelengths, and this causes the molecule to change shape. In rods, the conversion of light into a chemical signal is accomplished through a protein called rhodopsin, which is analogous to the pigment on a classic photographic film. Rhodopsin is a membrane protein that is localized to the discs in the outer segment of the photoreceptor. It's composed of a G protein-coupled receptor, opsin, and its ligand, retinal. Together they form the visual pigment rhodopsin. Retinal might ring a bell for some of you. Also called retinaldehyde or vitamin A aldehyde, it's one of the many forms of vitamin A. And it's the reason why eating vitamin A-rich foods, such as carrots, is said to have benefits for human vision. And also why vitamin A deficiency can lead to serious cases of blindness. Like any GPCR we've encountered previously in this course, the binding of a ligand to the receptor activates G proteins in the membrane, which in turn stimulates the downstream enzymatic generation of cytoplasmic second messenger molecules. It's the action of the second messenger molecules that can directly or indirectly change the conductance of ion channels, with the effect of changing the neuronal membrane potential. In this case, what differentiates rhodopsins from other GPCRs is the fact that its ligand retinal is already tightly bound to the GPCR protein backbone, opsin. When a photon is absorbed by retinal, the shape of the retinal changes from 11 cis retinal to all trans retinal. Here, cis and trans refer to the relative position of the side chains, but this conformational change in retinal also causes changes in the opsin backbone. The rest of the GPCR activation pathway is then very similar to what we've seen before. The changes in the opsin backbone cause activation of a G protein called transducin, which in turn leads to changes in the cytoplasmic concentration of second messenger molecules, in this case cyclic GMP, by the action of an enzyme known as cGMP phosphodiesterase, which lead to the modulation of cGMP-gated ion channels and changes in the membrane potential. Interestingly, in the absence of light, cyclic GMP normally opens sodium and calcium conducting ion channels in the outer segment of the photoreceptor, thus depolarizing the cell after sodium influx. Light actually depletes cyclic GMP in the outer segment, which has the effect of closing these ion channels and hyperpolarizing the cell. In other words, because photoreceptors hyperpolarize when light activates them, they release neurotransmitter in the dark and stop releasing neurotransmitter when illuminated. This is a bit counterintuitive and worth thinking about for a little while. It's worth pointing out that the light-stimulated conversion of 11-cis-retinal to all-trans-retinal is actually the only light-dependent step in the visual system, and the rest is just plain old chemistry and electricity. This crucial step was actually discovered right here at Harvard by George Wald, who received the Nobel Prize for his discovery, as well as his work on photopsins in 1967. One photon is actually sufficient to convert 11-cis-retinal to all-trans-retinal to initiate the phototransduction process. This is obviously a very dim pulse of light, so how is it possible for phototransduction cascades to have such a large effect on the neuron's membrane potential? If you recall from the previous modules of the course, one of the functional consequences of using a biochemical cascade for signal transduction is amplification. In this case, each activated rhodopsin can activate hundreds of G proteins, which in turn can activate many phosphodiesterases, which can in turn generate thousands of cGMP molecules. This amplification allows our visual system to detect as little as a single photon, and is also the reason why rods are specialized to function primarily well in dim hours of night.